Now we'll talk about the curl in curvilinear coordinate systems. First, let's recall the physical picture of the curl. The curl of a vector field is a vector which describes the local scale circulation of the field. And the local scale was important here, if you remember. Now, the integral definition of the curl is basically the limit as the c goes to 0, the path length goes to 0, closed path integral dr dot a. So we take the dot product with the displacement vector on a closed path in a small closed path. That's why it's local circulation. And then we divide it by the area. So it is the limit as s goes to 0, the surface integral d sigma. And if I take the dot product of curl A with this, I get the integration on the right hand side. So C is a closed path surrounding the surface S, and d sigma direction is determined by the right hand rule applied to the path C. So for this path here, so we are looking at Q1 hat and Q2 hat directions. So the if the circulation is in the counterclockwise sense, it's going to be, according to the right-hand rule, in Q1 hat direction. And here we have variation on the Q2 axis, so it's H2 dQ2, and variation on Q3 axis, so H3 dQ3 in Q1 hat direction. So this d sigma vector for this path is H2 dQ2 H3 dQ3 in Q1 hat direction. Then if I take the curl of A dot product with the limit as s goes to 0, the surface integral d sigma, this will be dQ2 dQ3 H2 H3 Q1 hat, which is my d sigma vector, dot product with curl of A. So I'm taking the component of curl of A on the Q1 axis. So this will be curl A dot product with Q1 hat. So this will give me, in other words, curl A's Q1 component. So here I have curl A's Q1 component from the dot product. All right. On the other hand, if I work on the right-hand side of this equation, the closed path integral dr dot a, that means I'm going through these CA, CB, CC, and CD segments to perform the integration. For CA and CC, let's see, for the integral on CA and the integral on CC, I have a variation on the Q2 axis, so it's H2 dQ2 multiplied with the component of the area vector on the Q2 axis, so this is A2, so H2 dQ2 A2 terms will appear. And for the segment B and D, I have variation on the Q3 axis, so it's going to be H3 dQ3 A3. So I have plus integral CB, and for CD, I will be considering H3 dQ3 A3. All right. And A2 vector, likewise, is A2 in Q2 hat direction, and A3 vector is A3 in Q3 hat direction. So what is the differential displacement vector on CA and CC? It is H2 dQ2 in Q2 hat direction, H2 dQ2 in Q2 hat direction, and for B and D, I have along these segments H3 dQ3 in Q3 hat direction. So that's what I have to consider. Now, let's concentrate on the segment CA. So the limit as C goes to 0 integral on CA, I have H2A2 product, H2A2. So where is this going to be evaluated? Now for this path, I have the smallest coordinates Q1, Q2, Q3. So this will be evaluated at Q1, Q2, and Q3. And that will be multiplied by dQ2. So H2 dQ2, H2 dQ2, dot product with the vector A, so it's the component on Q2 axis, and we are going in this positive Q2 direction. For CC, I'm going in negative Q2 hat direction, so this will be the same thing, minus H2A2. Now I have to be careful where to evaluate this. You see, I'm now at Q3 plus dQ3 on this path. So this has to be evaluated at Q1, Q2, Q3 plus dQ3, and it's multiplied by dQ2, but it's going to be in negative direction because the orientation of the path is, we're going in this direction, so it's in minus Q2 hat direction. The dot product will give me a minus sign here. So if I put these together for the segment on CC, let me first of all write the Taylor series expansion for H2A2 at Q1, Q2, and Q3 plus dQ3. This is going to be evaluated at dQ3 is equal to 0. So the first term here will be H2A2 evaluated at Q1, Q2, Q3. And then I have to take the partial derivative of H2A2 with respect to Q3, evaluated at the point dQ3 is 0, which is Q1, Q2, Q3, multiplied by dQ3. So now I'm going to add CA and CC integrations. So for the CA integration, I have H2, A2, dQ2. For the CC integration, I have the same thing with a minus sign. So there's a minus sign here. So this will cancel, and this term will remain with the minus sign. So when I put these together, the integral gives me minus del H2A2 del Q3 and dQ2 dQ3. So here we have H2 dQ2 A2, so that's what we are doing here. So H2 A2 evaluated at Q1, Q2, Q3 for CA, at Q3 plus dQ3 for CC, and I have this factor of dQ3 that comes from the Taylor series expansion, so this gives me minus H2 A2 partial derivative with respect to Q3 dQ2 dQ3. Now if I do the same exercise for CB and CD, let me look at the CB part here. For CB part, I'm at Q2 plus dQ2 on the Q2 axis. For CD part, I'm at Q2. So similarly, we can write for the CB axis H3 CB segment H3A3. Now this is at Q1 Q2 plus dQ2 Q3 multiplied by dQ3, and for CD I have minus H3A3 evaluated at Q1 Q2 Q3 multiplied by dQ3. So let me check. On D I have this axis, which is H3 dQ3, and I'm going in the negative direction, so it's in minus Q3 head direction is the orientation of this. So when I take the dot product, it will give me minus H3A3 dQ3 evaluated at Q1, Q2, Q3. Okay, so for H3A3 evaluated at Q2 plus dQ2, H3A3 evaluated at Q1, Q2 plus dQ2, Q3, I can again use the Taylor series expansion, which will give me H3A3 first evaluated at dQ2 is equal to 0. Q1, Q2, Q3. And then I have to take the partial derivative of H3A3 with respect to Q2 evaluated at Q1, Q2, Q3 multiplied by dQ2. So the similar story happens here. This term and this term will cancel out, and we're going to have only this term remaining. So in the limit C goes to 0 for CB plus CD, A dot dr gives me del H3A3 del Q2 dQ2 dQ3. Okay, so for H3A3 I have written this, and then I have dQ3. So this implies for the total limit as C goes to 0, closed path integral A dot dr, I have two terms from segments AC and BD. So one of the terms is del H3A3 del Q2. So this is the term I have here, and for the other one I have minus del H2A2 del Q3 minus del H2A2 del Q3, and this is multiplied by dQ2 dQ3. Okay, so this basically tells me that now I have to divide it by this term, H2 H3 dQ2 dQ3 in Q1 hat direction, the closed surface integral for the first component. So I'm taking the dot product, so curl A's first component. So let's put it together. Curl A's first component is, now this is going to be H2, H3, dQ2, dQ3. So I have to divide this result by H2, H3, dQ2, dQ3. So I'm going to get 1 over H2, H3, 1 over H2, H3. Now I have, let's take this here for the moment, partial derivative of H3, A3 with respect to Q2 minus the partial derivative of H2, A2 with respect to Q3. If I continue with the same thing for the second component, then I would have 1 over H1, H3. This time I will have partial derivative of H1, A1 with respect to Q3 minus the partial derivative of H3, A3 with respect to Q1. And as for the third component, I would have 1 over H1, H2. So I'm going through 2, 3, and then I have 3, 1, H3, H1. Let's write it this way. And then 1, 2, H1, H2. So I'm going in a cyclic mode. This would be partial derivative of H2, A2 with respect to Q1 minus the partial derivative H1, A1 with respect to Q2. So this gives me the components of the curl. First component, second component, third component, where I have the d sigma vectors parallel to Q2 hat and Q3 hat direction for these surfaces. And we can see that this set of equations is actually equivalent to the following determinant. So we could do this: 1 over H1, H2, H3. The determinant of H1, Q1 hat, H2, Q2 hat, H3, Q3 hat, partial derivative with respect to Q1, partial derivative with respect to Q2, partial derivative with respect to Q3, and we have H1, A1, H2, A2, and H3, A3. So it's equivalent to this. For example, for the first component here, we would have del H3, A3 del Q2 minus del H2, A2 del Q3. Now you can see here. Because I have H1, Q1 hat, H1s will cancel, so I would obtain 1 over H2, H3. So the first term would be recovered. We could also write this in subscript summation notation. Curl A, so we have to write Levi-Civita symbol epsilon ijk. We divide it by, so in the I hat, Q I hat direction, we have to consider I here. So if you see, it's in the, if you're looking at the first component, it's H2, H3. So this would be Hj, Hk. So Hj, Hk. Partial derivative of Hk, Ak with respect to Qj in Qi hat direction. Okay. So the gradient operator in curvilinear coordinates was given by this 1 over Hi del Qi in Qi hat direction. So here we're taking the ith component. So we have del del qj 1 over 8j, that gives me the gradient operator, and then the k component of a del hk ak divided by hk. So this is the generalized version for curvilinear coordinates in qi hat direction. So I can remember it this way. But this is basically the calculation we have to perform in order to get the curl in curvilinear coordinates. Okay, once again, we talked about the curl operation in curvilinear coordinates using the integral definition of the curl. We recall that curl means we're talking about the local circulation of a vector field. It's the limit as c goes to 0 dr dot a closed path integral and divided by the area limit as s goes to 0 surface integral d sigma. Now we have the dot product of this gives me this path integral. So I'm talking about the component of curl A in the direction of the area vector. And for I have only performed it for one of the surfaces here. So I have a closed path going from this point to back to that point in the counterclockwise sense. I have divided that into 4 segments, CA, CB, CC, CD, and carefully looking at the scale factor values I have to use for those displacements, I have realized that I can do the Taylor series expansion for this top one and also for not on this segment but on this segment where I'm at Q2 plus dQ2. Okay, so doing so, I have found that the CA and CC contribution is minus the partial derivative H2A2 dQ3 dQ2 plus dQ3. The direction of the area vector is determined by the right-hand rule. The right-hand rule tells me it's in Q1 hat direction. The area vector that I'm talking about here is H2 dQ2, H3 dQ3, so that's basically H2 dQ2, H3 dQ3 in Q1 hat direction. And the integration along the path gives me this answer, and for CB and CD I have a similar answer, and if I put them together I get this result. And when it's divided by the surface area, which is my H2 dQ2, H3 dQ3 in Q1 hat direction. Because it's in Q1 hat direction, I'm taking the component of curl A on Q1 hat. It's 1 over H2, H3, this expression. Now I realize that the set of equations I obtain considering this path for the area vector in Q1 hat direction, if I consider the situation when area vector is in Q2 hat direction and Q3 hat direction, I get similar results using cyclic permutations of 1, 2, and 3. For example, for the first component, I have H2, H3. It's H3, A2 with respect to Q2 and minus H2, A2 with respect to Q3. For the second component, 2, 3, 3, 1, 3, 1. So we have H1, A1 derivative with respect to Q3 minus H3, A3 derivative with respect to Q1, etc. So this set of equations is equivalent to this determinant 1 over H1, H2, H3, H1 Q1 hat, H2 Q2 hat, H3 Q3 hat, partial derivatives, and H1 A1, H2 A2, H3 A3. And this can also be written in Einstein subscript summation notation, epsilon ijk in Qi hat direction. This is curl. 1 over, because it's in Qi hat direction, I have Hj, Hk. And for the gradient operator here, I have del del qj. For the vector A, I have k component, but instead of k component, it's hk ak. And then it's divided by hk. So basically, this gives me the Einstein notation version of the curl in curvilinear coordinates.